Hi, welcome to Got Science. I'm Mike Zell. I've been reading about waves and I'm absolutely lost.
Attention all hands. Man overboard. Man overboard. This is not a drill.
Sim?
Ahoy there, Mike. Would you like some assistance?
You know it. That's Sim, the Got Science simulator. I'm having trouble understanding wave behavior, Sim.
It sounds like we should go over some basics. Let's get to work.
Ready when you are.
As a starting point, it's important to understand that waves are a form of energy. Do you see any waves in this baking dish, Mike?
No, the water's smooth.
Correct. But if we introduce kinetic energy in the form of a few drops of falling water, we can instantly create waves. The waves are simply another form of the energy carried in the droplets. And that energy is traveling through the water, which is referred to as a medium. Waves can also travel through other media, like air or the ground. When a scientist talks about waves traveling, they will say the wave has propagated, and some waves, called electromagnetic waves, can actually travel without a medium. Light waves, for example, which are part of the electromagnetic spectrum. But to keep things basic, for today, we'll focus on waves that travel through water.
What's that?
It's called a ripple tank, Mike, and it's very useful for demonstrating wave behavior. Right now, a small motor is generating a series of traveling waves. The motor acts like the drops of falling water, but it's more precise. I'm using slow motion here, so you can see the waves more clearly.
Why are they called traveling waves?
Because the energy carried by the waves is transferred from one location to another, so the energy travels. Here's a closer look at the pattern created by our traveling waves. This special screen displays the shadows created by the waves. Here's an illustrated view. Notice the crests and troughs and the medium at rest, which is the surface of the water undisturbed by the wave energy. Now what do you think happens when a traveling wave meets an obstacle?
It bounces off, right?
Yes, the wave will reflect off the surface of the obstacle, but in a very specific way. Let's say that the incoming wave strikes a barrier at a 45-degree angle. The resulting reflected wave will then travel away from the barrier at the exact same angle, 45 degrees. This is called the law of reflection. So tell me, Mike, what happens when a wave strikes a barrier straight on at 0 degrees?
Well, I guess it will reflect straight back in the opposite direction, 0 degrees, right?
Exactly, and that leads us to another interesting wave behavior called superimposition, which is the ability of waves to overlap. Can you see how it appears that the waves in the middle are standing still? That's due to superimposition of the incoming and reflected waves. This illustration should help clarify what's happening. You can see that the incoming and reflected waves are overlapped, but take a look at the positioning of the crests and troughs of each wave. They are not aligned and add together in a way that reduces the energy of both waves. The resulting wave is shown at the bottom. But as the waves move, the crests and troughs of the waves align differently. Presto, the waves now add together to reinforce each other. You can again see the resulting wave at the bottom. This alignment creates standing waves, or waves that appear to be locked in a fixed position. And here you can see how the resulting wave looks in our ripple tank, which proves that waves superimpose on each other when propagated in the same medium. Waves can exhibit many different behaviors, Mike. Today we've touched on just 2 of them. Keep studying, and let me know if I can help with anything else. Anchors away!
Thanks, Sim. And thank you for joining us today. For Got Science, I'm Mike Zell. We'll see you next time.